Hi everyone, today we're talking about sedimentology and stratigraphy again, and this is the fifth lesson in the Strat playlist on my channel here, and today specifically we'll be going over the texture or fabric of crystalline or endogenetic rocks, aka chemical rocks or chemical precipitates, and we'll specifically be going over cements, recrystallization fabrics, replacement fabrics, how to recognize replacement and recrystallization versus primary precipitation, and then we'll talk about crystallization in veins, the types of fabrics that might form from these crystals, and then lastly we'll go over oolites, pisolites, and spherulites, and a little bit over biogenic materials. So first, let's go over a little bit about clastic and chemical rocks and the difference between them, just to recap. In the last video, we discussed clastic textures or fabrics. Many rocks, or dare I say most sedimentary rocks, are both chemical and detrital. We can see here a clastic conglomerate in this figure to the top left, and what we know is that we classify that as clastic or detrital, but the stuff that holds it together, the cement in the tiny pore spaces between grains, is chemical. And so yes, we might say that it is clastic, but no rocks are fully clastic. We just classify them as such because they form in a more detrital fashion than they do a chemical fashion. But limestones are another type of rock that often contain both textures as well. As we can see over here, these examples of fossiliferous limestones are, yes, held together by chemical cement, but are actually detrital in nature because those fossil fragments were detrital grains that deposited and accumulated detritally or in a detrital or clastic fashion. So only pure precipitates that form primarily or during accumulation by precipitation from solution are fully crystalline, such as evaporites or actually igneous rocks, which aren't going to be discussed in this playlist. But if you want to know more about how igneous rocks crystallize from solution or magma, you can see my igneous petrology playlist. I'll link it up here to the right corner if you want to check it out. Now, if you've ever had a class on carbonate textures or carbonate fabrics, you've often heard the terms micrite, microspar, or sperry calcite. These are terms that are often used in the classification of limestones, but we actually won't be talking about these until we actually have the video all about limestones, and we'll have a whole playlist about carbonate petrology, and we'll get into those terms and talk about Folk and Dunham classification and all of that in those videos. But in today's video, we'll be focusing more on fabric or texture terms of carbonate or chemical rocks and precipitates. These types of terms include things like macrocrystalline versus meso, micro, and cryptocrystalline, and these terms are used to talk about the size of crystals. So if you remember in the grain size video of this said Strat playlist, we talked about size as it relates to detrital grains, in which the size terms were gravel, sand, silt, and clay. Whereas in this video, these are the size terms. But these aren't the only terms that we'll use to describe textures in crystalline or chemical rocks. There's also terms to describe whether the grains in the rock are equigranular or unequigranular. In terms of detrital fragments, we talked about this as sorting, so the sorting of grains. But when we're talking about chemical precipitates, it's not sorting because nothing's sorting the grains in terms of transport and movement. Instead, the grains are chemically precipitating where they are, and whether they're unequigranular or equigranular has nothing to do with transport. But if they are unequigranular, we have a couple terms to describe the clasts that stand out from the rest when there are big clasts in a smaller matrix. For example, if you have a big clast in a smaller matrix, you have a porphyroblast, or the texture is called porphyroblastic. If you have a big clast in a smaller matrix that has a bunch of inclusions in it, then that is called poikiloblastic. And if you've ever taken a metamorphic petrology class, you might recognize these terms because they're also used to describe metamorphic textures. And that's because metamorphic rocks and crystalline or chemical rocks are actually very similar. And we'll talk about why that is and their similarities as well as their differences on the next slide. But a couple more terms before we get there. So euhedral, subhedral, and anhedral are a few more terms we use to describe the grain shapes in these crystalline or chemical rocks. And euhedral means that the grain has well-developed crystal faces. So for example, this poikiloblast here has pretty well-developed crystal faces, whereas the fragments over here kind of just are filling the space rather than were formed, perfectly as the crystal shape that they were meant to be. They're kind of just filling an intergranular space, and these would be termed either sub or anhedral. And we'll show better pictures later of the difference between euhedral and anhedral and kind of what they might mean in terms of formation process. Lastly, grain boundaries are also important textural terms when it comes to crystalline rocks, and these grain boundaries can either be straight, curved, embayed, which is something we'll show on a later slide, scalloped or cuspate, which is exactly what it sounds like, or sutured. And we'll also show an example of sutured grain boundary on a later slide as well, and I'll point that out so you can see what that looks like. But to kick things off, let's start by talking about cement fabrics. So cement, if you remember from our previous Strat videos, is the chemical precipitation of typically things like calcite or barite in between the grain boundaries of detrital fragments or detrital grains, because those pore spaces are filled with solution, water, during, burial, because the burial is typically in an aquatic environment, and that water contains ions that if become saturated or under enough pressure, they can precipitate out in between those grain spaces and cement those grains together. Now, this is all happening during burial and during, pressure, compaction, and if burial becomes deep enough, there's a lot of similarities between what's going on here in terms of deformation, precipitation, and all that to metamorphic processes. And this is why the line between diagenesis and metamorphism is sometimes fuzzy, but we can draw a line if we say that clastic grains that aren't reacting with the cement or solution, basically the solution is precipitating out a cement in between the grains, but those grains themselves are not involved in the reaction, that can be defined as diagenesis, aka a sedimentary process. Whereas when conditions become so high temp and pressure that those clastic grains do begin to react with the solution and cement, then that can be defined as metamorphism. However, there are some exceptions when you have heavy sedimentary alteration that's not defined as metamorphism, where those clastic grains do react with the solution and cement. And that is typically an example of degradation or corrosion. Maybe there's acidic solutions or whatever it might be that cause those clastic grains to join in the reaction, but it's not necessarily under high temp and pressure of metamorphism. So there are exceptions, but in general, cementing minerals basically precipitate in pore spaces inward from the grain boundaries. So here's a little circle figure here that we can see. The crystals tend to start to precipitate at the grain surface and then form inward until they fill the pore space. As we can see here, the polka dots represent the clastic grains. The pore space is filled with crystalline fabric, and they tend to start by precipitating with a drusy or fibrous fabric, which is this kind of radial type of fabric of crystallization on the edge of those grain boundaries. And then as they move into the empty pore space, they get a bit blocky in their texture. However, many minerals recrystallize at normal pressures and temperatures, making it a sedimentary process, but the recrystallization can cause those detrital fragments to join in on, the reaction with solution and cement. And therefore, recrystallized minerals tend to have a different fabric than the cement itself. So we'll talk about recrystallization fabrics here, but there are a few different types of recrystallization to first define. Basically, recrystallization can sometimes only change the crystal structure of the mineral involved. For example, recrystallization from aragonite to calcite changes the crystal structure because aragonite and calcite have the same composition. They're both calcium carbonate minerals, but their crystal structure, or the way their atoms are arranged in those crystals, crystals is different. However, sometimes dehydration and or hydration is involved, in which case we have the example of gypsum to anhydrate. Gypsum and anhydrite both have the same composition. They are both calcium sulfate, although anhydrite does not have any water. It is dehydrated, whereas gypsum has water in its crystal structure. It is hydrated. And so when gypsum recrystallizes to anhydrate, it is becoming dehydrated. And lastly, we have compositional changes in some cases. For example, calcite to dolomite recrystallization causes a change from the composition being calcium carbonate to calcium magnesium carbonate or dolomite. And rocks don't have to be fully recrystallized. Sometimes they only partially recrystallize. And this recrystallization process tends to coarsen grain sizes. And for that reason, coarse calcite cements are hard to distinguish from recrystallized carbonate muds. For example, micrite or carbonate mud can form in between detrital grains and sediment. However, if we find big blocky calcite crystals or what's called spherulites in between those grains, we can't know for sure whether that spherulites was the original cement that precipitated or whether that was the result of finer grained carbonate mud or micrite that recrystallized into larger coarsened blocky calcite. Sometimes minerals can be fully replaced with other minerals, and both chemical and detrital grains can become replaced. But how can we tell the relative ages of mineral grains, or basically what formed first during or after deposition, and how can we use the fabrics of these chemical precipitates to tell? Well, cement is obviously younger or the same age as framework grains. So either as those framework grains were accumulating and becoming deposited, the cement was forming, or it formed after, so it's younger than those framework detrital grains. And that's a relatively easy relationship to see. Another easy relationship to see is that fracture and vugs are filled after the host rock was already formed. So the host rock forms, then fractures and vugs may form, or maybe they formed during the host rock's formation, but then they're filled, so like vein fillings, for example, are younger than that host rock. And that's another obvious relationship. But when it comes to fully crystalline material, how can we tell what's younger and what's older? Because we no longer have the detrital versus cement grains that we can look between, or the vug filling, or whatever it is. We have to see a fully crystalline fabric and try and get relative ages. In this case, we can look at grain shape. Remember those terms euhedral versus anhedral. We talked about how euhedral is a very well crystallized, or basically a crystal with well-defined crystal faces, whereas anhedral kind of just fills the interspace between those euhedral crystals. And so we know that the euhedral crystals probably formed first, probably with empty space to grow into, because they're like, hey, I got all this space to form well-defined crystal faces, whereas the anhedral stuff came in later because it's like, oh, I only can fill this space and then I'm taking up all the room, and I can't form my well-defined crystal faces because I don't have a full empty space to grow into. So anhedral crystals are typically younger than the euhedral ones. However, there are exceptions to this, and this is where it becomes a little bit more nuanced. You have to really look at the overlapping between grains to decide what is relatively younger and older. Basically, here we can see an example where euhedral minerals formed by replacement. That means they were younger rather than the typical rule, which is euhedral crystals being older. This fossiliferous limestone, or oolitic limestone, it looks like there's some oolites in there, which is something we'll define in a later slide, is becoming fully replaced by dolomite, or basically dolomitized. And that just means that fluid is flowing through it, or it's within a fluid that has a lot of magnesium, and that's altering the minerals in this limestone and replacing them with dolomite. So how can we recognize replacement versus authigenic or pore space precipitation? Well, replacement minerals often contain inclusions of the replaced minerals. So sometimes, like we saw with the poikiloblasts, they have a bunch of inclusions of the underlying material within them. And that means that they're typically formed by replacement. Another way we can look at it is the embayed contacts. So embayed contacts are indicative of replacement. And what these mean is basically these euhedral dolomite crystals are penetrating the previous crystal grains. And we could see that with some of these fossiliferous fragments are being penetrated by that replacement dolomite. And the last pretty easy way to tell replacement over authigenic formation is by looking for the typical pseudomorphs or pseudomorphic replacement minerals that are typically things like opalized wood, as shown here on the upper right corner, or dolomitized shells or limestones, like we see in this thin section here, or pyritized fossils, like we see in this brachiopod here. There's pyrite replacing the original material. And those are things that we know are formed by replacement because those are just, we know that wood isn't originally opal, and we know that shells aren't originally pyrite. So those are just things we know that they don't form primarily or authogenically. They have to form by secondary replacement. Next, I want to discuss vein fabrics. Veins are really cool because they can form in basically any rock type because, it's just like a fracture that's been filled, and they're typically fully or partially filled with minerals that precipitate from fluids flowing through them. So remember, fluids contain ions that if, get saturated enough in that solution, they'll start precipitating out, especially if they have a grain surface to precipitate on or just to nucleate their grains on and then start growing toward the interspace of that vein. Common vein minerals include gypsum, calcite, or quartz, and sometimes they're not acting alone. Sometimes you get veins that are filled by two or more of these minerals. For example, we have over here on the right a vein filled by quartz and calcite, and what we see is that the calcite seemed to start the filling of this vein or fracture here, and then later maybe solution came in that was more silica rich and it precipitated out quartz in the interspace between that partially calcite filled vein. And as we can see with this quartz calcite filled vein, sometimes vein crystals can be equal granular or blocky in their texture, but sometimes they can be fibrous or prismatic, as we can see this fibrously filled grain in the bottom middle figure here. Another thing to focus on in this image is the boundary between the crystals that formed from the top or bottom of this empty fracture that then met in the middle and formed a sutured boundary. Remember crystal boundaries? We talked about some of that terminology in the first slide, and we talked about sutured boundaries. This is an example of a sutured crystal boundary. But in general, vein fabrics typically can have similar fabrics to cements, for example, because cements are filling pore spaces in between grains, and they start at the grain surface and fill inward. Same thing is happening in vein fillings. Lastly, I want to talk about oolites, pisolites, and spherulites. Oolites and pisolites are only different based on their size. Oolites are smaller, they're from 0.25 to 2 millimeters in size, and pisolites are anything larger than 2 millimeters. So what are oolites and pisolites? Well, they're these spherical types of grains that form from accretionary growth around a nucleus or lithic or biogenic fragment that they use as their nucleus to grow material around. And this occurs by basically being in a swash environment where they're being swashed back and forth in a shore face environment. We talked about swash zone in the beach or shore face video. I'll link it up here if you want to check it out. But the swash zone basically swashes back and forth these nuclei, these lithic or biogenic fragments in a carbonate shelf environment, and in doing so covers them in carbonate material in this spherical shape with concentric layers that typically form due to events or episodes of accretionary growth. Another thing to note is that true oolites or true ooids are those that have two or more layers of material surrounding the nucleus, whereas superficial ooids are used to define those with only one layer of material covering the nucleus. And false or pseudo-oolites or oolites are those that lack internal structure. For example, maybe they're fecal pellets or micrite ooids that have just been deformed and replaced with micrite. These are called pseudo-ooids or pseudo-oolites because they're still spherical and they look like ooids on the outside, but internally they don't have the concentric or radial structure that comes along with ooids. And we can see a picture of such pseudo-ooids down to the bottom left, and these are typically called peloids because their origin is unknown. We're not sure whether they're just degraded microtized ooids or whether they're fecal pellets or whatever they might be. We just know they're not true ooids. And aragonite ooids often recrystallize to calcite, sometimes causing the ooids to lose their concentric structure, becoming massive or radial. And often calcareous ooids can be replaced by silica, dolomite, hematite, or pyrite. And spherulites are different from ooids in that they form in situ from chemical precipitation of radial crystals rather than accretionary growth around a nucleus. So spherulites don't typically have a nucleus and they don't swash around anywhere. They form right where they are in situ and often merge and have irregular surfaces in contrast to the very smooth calcareous surfaces of ooids. Now, in the last video, we talked about how fossil fragments are often incorporated in sedimentary rocks, such as limestone, for example, as clastic or detrital grains, and then they're cemented together. And so they have both clastic and chemical textures. However, the original primary material that those fragments are, those shells or skeletons, whatever they might be, were originally chemical because they formed from precipitation, typically from a process called biomineralization. And if you want to know more about biomineralization and how these biogenic minerals precipitate, then I actually have 5 different videos that you can go and look at. If you want to know specifically about like shell formation and how organisms control the precipitation of their skeletons or shells, I recommend the 5th video because that's actually about biologically controlled biomineralization of things like calcite, for example. The 4th video is also good for that because I talk about silica skeletons and shells in that one. But for this video about the fabric of chemical sedimentary rocks, that is all I have for my references. I used the Sedimentology and Stratigraphy book by Boggs and Sedimentary Rocks by Pettyjohn, and these are both linked in my description below if you want to check them out, as well as other minor and supporting references. And if you want to check out the rest of the topics listed here for this Strat playlist, the 4 above the white arrows are previous videos I've already done that kind of come before this one, which is represented by the white arrows here, and the ones below the white arrows are ones that are coming up in this playlist. And by the time you're watching this, maybe they're all out by now, so you can click the rectangle down below that says Strat playlist to see if any or all of those videos are out and watch more if you're interested. But thank you so much for watching this one at least, and I hope you enjoyed and learned a lot, and I will see you guys next time. Bye.